Welcome class to our guided notes on Skill 6 from Unit 4. This skill focuses on radical signs and how to simplify them, and not just square roots, but roots with any type of index, which is indicated by this little teeny number written out in front of the radical sign. Will tell you what root we're taking. So this over here is just a little graphic to help you know what to call everything. So that little number we see out in front, we refer to that as the index. And then this symbol right here, we call the radical sign. And so oftentimes I'll just refer to it as rad whatever, and we call them radicals. And we are learning how to simplify them today. And then the quantity that's underneath the radical sign is referred to as the radicand. So sometimes when I just want to talk about the inside of the radical, I will refer to it as the radicand. Now over here in examples 1, 2, and 3, I want you to basically find the index and then see if you could figure out the value. So in number 1, the index is 3. It's that little number written out in front of the radical sign. And what that means is that we're trying to find the cube root. And what that means is we're trying to figure out what number would it be that multiplies to itself 3 times to equal 27. Like, that's what we're trying to figure out. What number would that be? That if I multiplied it to itself 3 times equals 27. So hopefully you guys are thinking about it right now. That number is 3. So 3 would be the result of this radical, because it's the number that if I multiplied it to itself 3 times, which matches the index, it would equal the radicand, the thing under the radical sign. In other words, this is another way of saying the cube root of 27 equals 3. In number 2, we see an index of 5. And so it has the same meaning, except now we're looking for a number that would have to multiply to itself 5 times. Same identical number multiplied over and over 5 times. 1, 2, 3, 4, 5 to equal -1. That's what we're trying to find out. Like, what number is that? So, any ideas? Hopefully you're thinking about -1 is its own 5th root, because -1 times -1 is positive. +1 times -1 is negative. -1 times -1 would be positive again, and then times a 5th -1 would go back to equaling -1 again. So this is the number that if I multiply it to itself 5 times equals -1. It's the 5th root of -1. Okay, now here you might say, well, that looks familiar, because that's what you've been working on since Algebra 1 is radical signs without an index. So when there is no index, we default to a square root. So basically the default, the radical sign with no index, is a square root. That's when you look for a number that would have to multiply to itself twice, right? This number times itself equals 9. What is that number, right? That's what you have to kind of ask yourself. What's the square root of 9? What number times itself 2 times equals 9? And that number is 3, right? Because 3 times 3 is 9. So basically, the index is also referring to the root. What root are we looking for? This was a 3rd root or a cube root. This is a 5th root. This was a square root. And by root, we mean a number multiplied to itself that many times to equal this result, 27, -1, and 9. Okay, so for the rest of the examples on this outline, we're going to be using one of 2 methods. In both of the methods, though, we have to break the number down into factors, right? Both of them begin the same way. Method 1 kind of focuses more on the size of the index and then grouping things according to that size. Whereas method 2 focuses more on looking for numbers that are perfect squares or cubes. So it doesn't necessarily go all the way down to the prime factors like method 1 does. But both of them end with simplifying to take stuff outside of the radical which is basically the perfect roots or the perfect squares. You end up taking the root either way, and the root ends up outside the radical. And then sometimes things are left inside, so that's okay. We leave them inside. And the answer is always a product. A product of the perfect root that we took out times whatever is remaining underneath that radical sign. So let's begin. Let's try it with example 4. In example 4, there's no index shown. So then what we are to understand is that it is a square root, right? A square root is the default root. So we're looking for perfect pairs, right? Perfect pairs. Two identical numbers that multiply together. So I start by just taking 50 and factoring it, right? I can see it breaks into 25 and 2, and 25 breaks into 5 and 5. So I see right there a perfect pair, right? Two of the same number. So we can think of the square root of 50 as the square root of 5 times 2. And we notice a perfect pair. And that grouping of 5 indicates a perfect root. That is what it said here in our steps, that an index-sized group indicates a perfect root. And that's what we have with 5 and 5. It's the size of 2, right? Matches the index. So that's a perfect square. And so 5 would be the square root. So method 1 would have you go one step further and write this as 5 squared times 2, and recognize that now you have a perfect square, which matches my square root. And then in a sense, they sort of cancel each other out, right? Perfect square. I'm square rooting a perfect square. That's just going to equal 5. So I can take a 5 out of the square root because it's a perfect root. And then I have to leave the 2 inside the square root because there was only one of them, right? The only way you can take something out of a square root is if it's a perfect pair. But when you have a single factor, it has to stay inside. So that's the answer using method 1. And let me just kind of show you what method 2 would be. Method 2 starts the same way. You break 50 into the factors of 25 and 2. But then method 2 says, well, I know that 25 is a perfect square, so I know what the square root of it is. It kind of square roots it separate because this is a product, and so you can square root separately over a product. And the square root of 25 is 5, and the square root of 2 is not a perfect square, so we just leave it as that. But it's basically the square root of 25, which is 5, times the square root of 2, which is the square root of 2. So you see either way, you get the same answer. Method 1 is nice for when things start getting more complicated. You keep track of things based on the index size. It will help you for the more complicated ones. Method 2 is really great though for the easier ones. Like right away, if I see, oh, 50 is 25 times 2. Okay, square root of 25 is 5. Okay, 5 rad 2. Like you can get to the answer a little faster with method 2 for the simpler examples like number 4. Okay, let's move on to number 5. Now you may notice in number 5, my index is now a 3. So I'm looking for perfect trios, basically. I'm looking for groupings of 3 of the same number, 3 identical numbers. So we start by factoring 108, however you want to. And because it's an even number, maybe I'll start by just dividing it by 2. 2 goes into 10 5 times, it goes into 8 4 times. So 2 and 54. I recognize that 54 is another even number, so I can divide that by 2. And it's 2 and 27. Now you might be recognizing 27 as a perfect cube, but if not, we continue to move on, and that can divide by 3 and 9, and then 9 can break into 3 and 3. So method 1 would have you write it this way. The cube root of 108 is equal to the cube root of, and then we can write it in terms of these prime factors, 2 times 2 times 3 times 3 times 3. And then you might recognize here's a perfect trio, right? A grouping of 3 identical factors, that's a perfect cube. Okay, I want to bring it back to this step. It's an index size group, so that indicates a perfect third root. Okay. And then to really sort of drive the point home, we can think of this as 2 squared and 3 to the third. And we notice that the exponent of 3 matches the root, right? The index matches the power, indicating once again that 3 is a perfect cube root, right? And I'm taking the cube root of a perfect cube, and I end up with just getting 3. Whereas 2 is not a perfect cube, so the 2 squared will have to stay underneath the cube root sign. So then this will equal 3 times the cube root of 4. 2 times 2 is 4. That's my final answer. I could take out 1, 3, because that was the cube root of 27, or the cube root of 3 times 3 times 3. That indicates a perfect root of 1, 3, so I bring that out. 2 times 2 is not enough, right? It only had 2. I needed a perfect trio, so those had to stay in, and then we just sort of multiply them back together. So that's our answer. Let me just kind of show you how method 2 would work in this case. So you'd still have to factor the 108 like we did, but maybe when you get to the 27, you could stop and go, okay, here's what I noticed. The cube root of 108 is equal to 2 times 2 times 27, or 4 times 27, and 27 is a perfect cube. And I know the cube root of it, so I will take the cube root of it, right? Cube root of 4 times cube root of 27, and we know this to be 3. So we just evaluate it and say, well, that's 3, and I'm multiplying that to the cube root of 4. That's the other way to think about it. Either way, you should end up with a 3 outside of the cube root and a 4 underneath the cube root, and the answer is the product of the perfect root times the radical with the remaining factors inside. Moving on to number 6, you may notice that now we have an index of 4. So I'm looking for perfect groups of 4. Maybe I could call that a quartet, right? Perfect quartets, groups of 4 identical factors. And so I begin by factoring 80. Maybe I'll just do 8 and 10. And then I can break 8 into 4 and 2, and then I can break 4 into 2 and 2. 10 I could break into 5 and 2. So here's what I notice. I've got factors of 5 and 2, and then 2 and 2 and 2, right? 2 times 2 times 2 times 5 times 2. So what I can do is write it this way. The 4th root of 80 is equal to the 4th root of, I've got 4 2's, 1, 2, 3, 4. 2 times 2 times 2 times 2, and then I have a single 5 times 5, right? And then just to, kind of bring it back to my factor tree, this was 8, and that was 10, just so you can see the multiple ways of writing products, right? 2 times 2 times 2 is 8, 2 times 5 is 10, 8 times 10 is 80. So this is just another way of writing 80. It's really 4 2's and a 5, which works out great for us because I needed a perfect quartet. I needed a perfect grouping of 4. So that means I have a perfect 4th root, basically. My perfect 4th root is 2. That's what that means. So method 1 would then have us write it that way, 2 to the 4th, to show me it's a perfect power of it's a perfect 4th root times 5. And then we notice, well, the exponent of 2 matches the index. It's a perfect size group to indicate that 2 is a 4th root. So I can take 2 out. It's a perfect 4th root. It's being raised to the 4th power, and I'm 4th rooting it. In a sense, they sort of cancel each other out and leave me with just a 2. But for the 5 is to the 1st power, so that one doesn't cancel out, and it's still a 4th root of 5. And so there's my answer for that one. That's kind of the method 1 approach. Method 2 would maybe look at the factors of 80 differently and say, well, if the fourth root of 80 is 4 2s and a 5, we could think of that as 16 times 5, right? Because 16 is 2 times 2 times 2 times 2. And 16 is a perfect fourth root. And so we could think of this as the fourth root of 16 being multiplied to the fourth root of 5. And we know the fourth root of 16 to be 2 because we know that 2 times 2 times 2 times 2 is 16. So then that is 2, and I'm multiplying it to the fourth root of 5, which is not a perfect fourth root, so I just leave it as the fourth root of 5. And there is my answer. So you see the answer is the same regardless of which method you use. It's just kind of a different way of thinking about it. Now number 7 is special because I have added in some variables, and here's where method 1 will come in really handy in terms of writing things raised to different exponents. Now the x and the x and the y are already written to their powers, so we don't need to really factor those. The 32 we'll have to look at the factors of. Well, I can see it's an even number, so I will divide it by 2. 2 times 16 is 32, and then 16 can break into 2 and 8, which can break into 2 and 4, which can break into 2 and 2. So it turns out that 32 is actually a perfect fifth power, basically. 2 times itself 5 times. 1, 2, 3, 4, 5 equals 32. So let's rewrite this that way. So we've got 2 times 2 times 2 times 2 times 2, right? 2 to the 5th power. I might split up the x, though, into x to the 5th and x squared. As a quick reminder, when you're multiplying x's to different powers, the powers add. So x to the 5th times x squared would be x to the 7th. Maybe I'll write that as a little side note right here. So that's a property of exponents. I'm using it backwards. And then the y, I'll think of that as y to the 5th, y to the 5th, and then y to the 1st. Because I'm trying to get things in terms of 5, right? I'm trying to get index-sized groups. And actually, this is going to be one in a second. So let me rewrite that. I've got the 5th root of 2 to the 5th, because I had 2 times 2 times 2 times 2 times 2, 2 to the 5th, times x to the 5th times x squared, because 7 is 5 plus 2, times y to the 5th times y to the 5th times y to the 1st, because 5 plus 5 is 10, plus 1 is 11. And what I've done is I've arranged everything into index-sized groups, and I notice I have 4 perfect roots of 2, x, y, and y. Because these are indexed-sized groups, so they're each perfect roots. They're perfect fifth roots. Whereas x to the squared is not enough x's, right? There's only 2 of them, and I need 5. And same with y to the 1st. There's only 1 of them, and I need 5 to pull out a perfect root. So I will do just that. I'll take out a 2. I'll take out an x. I'll take out 2 factors of y. Because each of these, in a sense, cancel, right? A 5th root of a 5th power, right? They all cancel. But the 5th root of x squared does not cancel, and the 5th root of y to the 1st does not cancel. So those stay under a radical sign with a 5th root. And then I can multiply all of these outside numbers together. So that just equals 2xy squared times the 5th root of x squared y. Now I don't need to write a multiplication symbol because in math, when you write things right next to each other, that implies multiplication. So this is one large product. Okay, I want you to remember that. The numbers I brought out were perfect 5th roots. The numbers that stayed inside were not. Lastly, I wanted to do an example where there's already a number written outside the radical sign. So there's a number outside already. So basically, all you'll have to do is when you begin simplifying the radical, and if you bring anything from the inside of the radical out, you will need to multiply it to the 7. Okay, so let's start by simplifying this radical. We'll start by looking at the factors of 96. So 96, it looks like it can divide nicely by 3. So 3 goes into 9 3 times, it goes into 6 twice. 32 we know can break into 2 and 16. I see my perfect square right here, right? 16 can break into 4 and 4. And yes, I can break the 4s down further, but I won't because I already see my perfect pair right here. Okay, so what I have is 7 times the square root of 3 times 2 times 4 times 4 times x squared times x, right? Because this is x to the first. So side note, little side note over here, x to the third is equal to x squared times x to the first, because when you're multiplying x's, you add the powers. 2 plus 1 is 3. Okay, so I can think of that as 7 times the square root of 3 times 2 times 4 squared times x to the first. So these indexed size groups right here, 4 squared and x squared, right? These guys indicate my perfect pairs, my perfect square roots to match my index. So those perfect roots are going to come out of the radical sign and they are going to multiply to the 7 that was already there. So I'll have 7 times 4 times x on the outside of the square root. Meanwhile, on the inside, I had a single 3, a single 2, and a single x, and those have to stay under the radical sign and multiply together. 3 times 2 times x is 6x. And then lastly, I can multiply the 7 and 4 together and get 28x on the outside of the square root times 6x underneath the square root. And then that's my simplified answer for number 8. So what I'd like you guys to do here is pause your video and try these 2 examples down at the bottom and come back and check your answer when you're done. Okay guys, welcome back. So for you try number 1, I got 8xy on the outside of the square root and then a single xy on the inside of the square root. So it was 8xy times radical xy for my final answer. For number 2, I had to factor 80 and I got it into 2 times 2 times 2 times 2 times 5. I think we did that earlier, so it's the same factors. 4 2s and a 5. Recognize that 2 to the 4th was a perfect fourth, a perfect quartet, right? I wrote that as a power, 2 to the 4th. And then I had a couple other perfect quartets, right? 4 factors of x and actually 10 total factors of y, which could break into 2 perfect quartets and then 1 pair, y squared. So y to the 4th, y squared, and a quick note, that all adds up to y to the 10th because the y's are being multiplied together, so we add the powers. And I broke it into 4 and 4 and 2 because I was looking for index-sized groups. And there were 2 perfect quartets of y. So for that reason, I was able to pull out 2 factors of y as my 4th roots. So I had 2 4th roots of y, 1 4th root of x, 1 4th root of 2, pulled all that out. But I only had a single factor of 5 and then only 2 factors of y left over in the other 2 groups. So those had to stay underneath the 4th root sign. So my final answer was 2xy squared times the 4th root of 5y squared with just a little asterisk. So this example actually requires an extra step, which we won't learn about until our next video, which will be posted on Canvas tomorrow. So stay tuned for what else is required for an example like number 2. I wonder what it could possibly be. Anyway, so I want you to try the practice problems now. Let me know if you have any questions, and thanks for listening.